In this video, we will continue our discussion of L'Hopital's rule, specifically investigating an additional type of indeterminate form. But as a reminder, suppose we would like to evaluate the limit given here. If the limit of the top and the bottom are both 0, that would be we have an indeterminate form of type 0 over 0, then we can apply L'Hopital's rule to find that the limit is equivalent to where we differentiate the function in the top and we differentiate the function in the bottom. And another indeterminate form would be when the top and the bottom function are both going to plus or minus infinity. It could be either of those, plus or minus infinity, and we call this an indeterminate form of type infinity over infinity. Let's now look at kind of a motivating example. The limit as x approaches 0 from the right of x times natural log x. Once again, our visual intuition is very important here. So to the side, let's graph natural log x. So natural log x, roughly speaking, looks something like this. So it crosses the x-axis at 1. And two important limits related to the natural log of x would be that the limit as x approaches infinity of the natural log is infinity, and the limit as x approaches 0 from the right is minus infinity. So with this in mind, as x approaches 0 from the right, x itself goes to 0, and the natural log goes to minus infinity. And this is an indeterminate form of the type we'll call 0 times infinity. And the idea is somehow what we would like to do is relate back to these two first cases of L'Hopital's rule. And how we are going to do so is we are simply going to rewrite x times the natural log of x. So this is equivalent to just algebraically rewriting the natural log of x divided by 1 over x. And recall that this is algebraically equivalent because dividing by a fraction is the same thing as multiplying by its reciprocal. So dividing by 1 over x is equivalent to multiplying by x. Now, why have we done this? As x goes to 0 from the right, ln of x, a moment ago we said goes to minus infinity, and 1 over x, as you approach 0 from the right, goes to positive infinity. So this is an indeterminate form of type infinity over infinity, which means we can apply L'Hopital's rule. Now, one small bit of intuition here. When we have rewritten going from x ln x to natural log x divided by 1 over x, we could have put this in an indeterminate form of type 0 over 0 by instead having x divided by 1 over ln of x. I chose to rewrite it in this way because 1 over x is easier to differentiate than 1 over ln of x. So now, applying L'Hopital's rule, we have the limit as x approaches 0 from the right, we differentiate in the top, 1 over x, and we divide by the derivative in the bottom, minus 1 over x squared. And this very conveniently simplifies down to the limit as x approaches 0 from the right. And remember, dividing by a fraction, like say 1 over x squared, is equivalent to multiplying by its reciprocal, in this case, x squared. So this is the limit as x approaches 0 from the right of minus x, which is equal to 0. So let's investigate another example. The limit now as x goes to minus infinity of x squared e to the x. And once again, to start building up that visual intuition, let's sketch the graph of e to the x. So e to the x roughly looks something like this. So as x goes to minus infinity, so we're thinking out here to the left, e to the x is going to 0. But x squared, if you think of it as a parabola opening upwards, is going to infinity. So we once again have one of these indeterminate forms of this type 0 times infinity. which means we can rewrite algebraically by dividing by the reciprocal of one of these two functions to get an indeterminate form of type 0 over 0 or infinity over infinity. So this is the limit as x approaches minus infinity, and how I'm going to rewrite it is x squared divided by 1 over e to the x. And the reason I chose to rewrite it in this way is because 1 over e to the x is simply e to the minus x. And graphically, e to the minus x would be a reflection of the graph y equals e to the x about the y-axis. So in red here would be the graph y equals e to the minus x. So as x goes to minus infinity, x squared is still going to infinity, and e to the minus x is also going to infinity. So we have one of L'Hopital's indeterminate forms of type infinity over infinity, which means we can apply L'Hopital's rule. So this will be the limit as x approaches minus infinity. We take the derivative in the top, divide it by the derivative in the bottom, where here we've differentiated via the chain rule. And we play the same game again. Now as x goes to minus infinity, the top goes to minus infinity. And the bottom is going to, because it's a negative e to the minus x, also minus infinity. And as a reminder, they do not, the top and the bottom both do not need to go to the same plus or minus infinity, just one of them. But we apply L'Hopital's rule now a second time. This will become the limit as x goes to minus infinity, 2, divided by, and when we differentiate in the bottom again, we'll have minus and minus, so this becomes e to the minus x. The bottom is still going to infinity. Dividing a number by something which is getting really big is going to give us a limit of 0. Remember, dividing by something big gives you back something small.